Hi all, welcome back to my channel. We will learn functions and pointers in this video.
Welcome. Today we're diving into functions and pointers, two fundamental concepts in programming. These tools help us write efficient, flexible code. We'll explore how they work, why they matter, and how to use them effectively. Let's get started with Unit 4 from the Jerusalem College of Engineering. A function is a block of code designed to do one specific job. Instead of repeating the same lines over and over, we write the code once inside a function. Then, whenever we need that task done, we just call the function. It's a way to keep our code clean, efficient, and easy to manage. Functions help us avoid duplication and make our programs more organized. Here's a simple example of a C program. It starts by including the standard input-output library, which lets us print messages to the screen. Then, we define a function called greet that prints "Hello, students." In the main function, we call greet to display that message. Finally, the program ends by returning 0, signaling it ran successfully. This example shows the basics of defining and using functions in C. Let's talk about what it means when we say greet is a function. A function is like a little machine. It does a specific job. When we write greet with parentheses and a semicolon, like greet, we're telling the machine to start working. That's when the greet function runs, carrying out whatever task it's designed to do. It's a simple but powerful way to get things done in code. Functions bring several key advantages to programming. First, code reusability. We write a piece once and use it multiple times wherever it's needed. Then there's modularity, breaking a large program into smaller, manageable modules. This makes debugging easier, since we can test each function independently. It also improves readability, helping us and others understand the program more clearly. Finally, functions make maintenance simpler. Changes happen in just one place, saving time and reducing errors. When we talk about a function definition, we mean the part where the actual work happens, the body of the function. It's where the instructions live. The syntax usually starts with the return type, followed by the function's name, and then the parameters in parentheses. Inside the curly braces, we put the statements that tell the function what to do. This is the core of any function, the blueprint for its behavior. Let's break down this simple function step by step. First, we see the return type int, which tells us the function will give back an integer value. Next is the function's name, add. Inside the parentheses, we have the parameters, 2 integers, and the curly braces mark the function body, where the actual work happens. Here, sum is assigned the value of a plus b. Finally, the function returns sum, sending the result back to wherever it was called. This is the basic structure of a function in action. When we want to run a function, we use something called a function call. It's like giving the function a command to do its job. For example, we might write result equals add 10, 20. What happens next is the function receives those numbers, 10 and 20, assigns them to variables, adds them together, and then returns the sum, which is 30. That value gets stored back in result. It's a simple but powerful way to reuse code and get things done.
A function prototype is like an early announcement to the compiler. It lets the compiler know a function exists before we actually use it. It tells the compiler the function's name, what kind of value it returns, how many parameters it takes, and the types of those parameters. The syntax looks like this: return type, function name, then parameter types in parentheses. For example, int add, int means there's a function called add that takes 2 integers and returns an integer. This helps keep everything organized and clear.
Here's a simple example of a C program that adds 2 numbers using a function. First, we declare the function prototype. That's just a promise to the compiler about the function's name and parameters. Then in main, we call this function with 2 values, 10 and 20, and store the result. Finally, we print the sum. The function itself is defined after main, where it takes 2 integers and returns their sum. It's a clear way to separate logic and keep code organized. Let's break down 3 key concepts in working with functions. First, the function prototype. It's like a promise to the compiler. telling it what the function looks like without giving all the details. Next, the function call. This is where we actually ask the function to do its job, passing in values. Finally, the function definition here, where the real work happens, the code that adds two numbers and returns the result. Together, these parts make functions clear and usable. Let's look at a common situation in programming. Here, the function add is defined after main. But when the compiler reads main and sees add being called, it doesn't know what add is yet. That causes a problem. To fix this, we declare the function before main. This is called a function prototype. It tells the compiler what to expect, so it's ready when the function is called later on. This is why function prototypes are needed. When we pass data to a function, there are two main ways to do it: pass by value and pass by reference. It's important to know that in C, we technically only use pass by value. What people often call pass by reference in C is actually done by passing the address of a variable, using pointers. This subtle difference shapes how data moves and changes inside our functions. Let's explore what that means in practice. Here's a simple example of pass by value in C. We start with a variable, a set to 10. Then we call a function, change, passing as an argument. Inside the function, the parameter gets a copy of A's value. When changes to 100, it only affects that copy. The original variable stays the same. This shows that with pass by value, modifications inside the function don't impact the variable outside. It's a fundamental concept for understanding how data moves in functions. Let's look at what happens when we run this code. We start with a set value of 10 for when the function is called. It gets a copy of that value, not the original. Inside the function, x changes from 10 to 100. But once the function ends, it remains unchanged at 10. That's because the function only works with a copy, so the original variable stays the same. This shows how passing by value protects the original data. Let's look at how pass by reference works in C. Instead of passing a copy of the variable, we pass its address, a pointer to the original data. This means any changes inside the function directly affect the variable outside. In this example, the function change takes a pointer to an integer, then updates the value at that address. When we print the variable afterward, we see the updated value, showing the original variable was modified through its reference.
Here, we're looking at how the original variable gets changed through a function. When we call change with and we're passing the address of not its value. Inside the function, x is a pointer holding that address. So when we write x equals 100, we're saying, go to the address x points to, and update the value stored there to 100. That's why after the function runs, itself becomes 100. It's a way to directly modify the original variable through its memory address.
When we talk about passing data in programming, there are two main ways to do it: pass by value and pass by reference. Pass by value means a copy of the data is given to the function. The original stays safe and unchanged. Pass by reference, on the other hand, passes the address of the variable, so any changes affect the original data. Pass by value is safer when you want to protect your data. Pass by reference is handy when you need to modify the original directly.
Here's an example showing how passing by value works in C. We have two variables, x and y, set to 10 and 20. When we call the swap function, it only swaps copies of these values, not the originals. So, even after the swap function runs, x and y remain unchanged. This is because the function works with local copies, not the actual variables. It's a key concept to understand when dealing with function arguments.
Here, we're passing the addresses of x and y to the function. That means the function can directly modify the original variables, not just copies. Inside the swap function, pointers let us access and change the values stored at those addresses. We use a temporary variable to hold one value while we swap them. This way, when we print x and y after the swap, their values have actually switched places. It's a simple but powerful use of pointers.
Recursion is a programming technique where a function calls itself to solve a problem. It's a powerful way to break down complex tasks into simpler ones. But there's a catch. Every recursive function needs a base condition. This base condition stops the function from calling itself endlessly. Without it, the program would run forever. The general structure is straightforward. Check the base condition first. And if it's not met, call the function again. This cycle continues until the base condition is satisfied.
Let's talk about factorials, a fundamental concept in math and computer science. The factorial of a number, written as n factorial, is the product of all positive integers from n down to 1. For example, 5 factorial is 5 times 4 times 3 times 2 times 1, which equals 120. This slide also introduces how we can calculate factorials using recursion, a powerful technique where a function calls itself to solve smaller instances of the same problem.
Here, we see a simple C program that calculates the factorial of a number using recursion. The function calls itself, multiplying the current number by the factorial of 1 less than that number. When it reaches 0, it stops. That's the base case. In this example, it calculates the factorial of 5, which is 120, and then prints the result. This shows how recursion can elegantly solve problems that involve repeated, nested calculations. Let's break down how the factorial function works with the number 5. We start by multiplying 5 by the factorial of 4, then 4 times the factorial of 3, and so on. This process keeps going until we reach factorial of 1, which is just 1. When we multiply all these numbers together, 5, 4, 3, 2, and 1, we get 120. This step-by-step breakdown shows how the function executes, building up the final result through repeated multiplication.
Let's talk about pointers, a key concept in programming. A pointer is simply a variable that holds the memory address of another variable. For example, if we have an integer with the value 10 and a pointer p, we can store the address of a in p, so a holds the value 10, and a gives us the address of a p stores that address, and p lets us access the value at that address. Pointers let us work directly with memory, which is powerful.
Let's talk about pointers, a fundamental concept in programming. A pointer is declared using the star operator, placed between the data type and the pointer's name. For example, int star p declares a pointer to an integer. You'll see similar declarations for floats, chars, and doubles. It's important that the pointer's type matches the kind of data it's meant to point to, because that ensures the program handles the memory correctly. This is the basic syntax for defining a pointer. Now, let's take a look at the program. This is our roadmap. The sequence of topics and activities we'll explore together. It's designed to build understanding step by step, so each part connects smoothly to the next. As we move through the program, you'll see how every piece fits into the bigger picture, helping us reach our goals efficiently and clearly.
Let's talk about how we initialize a pointer with the address of a variable. Here, we have an integer variable, a set to 10. Then, we declare a pointer, p, and assign it the address of a using the address of operator, the ampersand. So p holds the memory address where a lives. When we dereference p, that is, use asterisk p, we get back the value stored in a, which is 10. This is the basic idea behind pointer initialization. Here, we have a simple C program that demonstrates pointers in action. We start by declaring an integer variable, and assign it the value 10. Then, we create a pointer, p, which stores the address of the program, prints out the value of its memory address, the value of the pointer p itself, and finally, the value that p points to. This example clearly shows how pointers can access and manipulate data indirectly through memory addresses. Let's talk about two important operators in programming, starting with the address of operator, represented by the ampersand. This operator gives us the memory address of a variable. For example, if we have an integer variable, a set to 10, using the address of operator lets us print where a is stored in memory. This is key when working with pointers, as it helps us directly access or manipulate data by its location, rather than its value.
Let's talk about the dereference operator. It's what lets us access the value stored at a specific memory address. Imagine we have a pointer p that holds the address of a variable a. When we write p, we're saying, give me the value stored at the address p points to. So, and a gives us the address of a. P holds that address, and P fetches the actual value there. It's a simple but powerful way to work directly with memory.
Pointer arithmetic lets us do math directly with pointers. The most common operations are increment and decrement, moving forward or backward through memory. We can also add or subtract values and compare pointers to see their relative positions. For example, if we have an array of integers and a pointer set to its start, incrementing that pointer moves it to the next element. This lets us navigate arrays efficiently, using simple math on addresses.
Let's look at what happens when we work with pointers and arrays. Initially, the pointer p points to the first element of the array, r, 0. When we write p++, we're telling the pointer to move forward by one element. So, before p++, p points to the value 10. After p++, it points to the next element, which is 20. This simple increment moves the pointer along the array, stepping through each element one by one.
Here's an important detail about pointers in C when p is a pointer to an int. Doing p++ doesn't just add one byte to the address. Instead, it moves to the next int in memory. So, if an int takes up 4 bytes, and p points to address 1000, then p plus 1 points to 1004, and p plus 2 points to 1008. Keep in mind, the actual size of an int can vary depending on the system and compiler. Pointers and arrays in C are tightly connected. When you use the name of an array in an expression, it usually becomes a pointer to the first element. For example, if we have an array of 4 integers, the name of that array points to the address of the first item. So, when we write a pointer and assign it the array name, it's the same as assigning it the address of the first element directly. This relationship is fundamental to how C handles arrays and pointers. Here, we see a simple C program that demonstrates how to access array elements using pointers. We start with an array of integers, then create a pointer pointing to the first element. The for loop iterates through the array by moving the pointer along, using pointer arithmetic to access each value. This approach shows how pointers and arrays are closely connected in C, allowing us to navigate data efficiently without using the array index directly. It's a fundamental concept that unlocks powerful memory management techniques. When we access an array element using R with square brackets, like Ri, it's actually the same as using pointer arithmetic, R plus I. So R2 and R plus 2 both point to the same value. In this example, that value is 30. This equivalence shows how arrays and pointers are closely connected in how they work under the hood. It's a simple but powerful idea to keep in mind. Let's take a closer look at how arrays and pointers relate to each other in C. Imagine we have an array of 3 integers, 10, 20, and 30. If we set a pointer to the start of this array, dereferencing that pointer gives us the first value, 10. Moving the pointer by 1 position gets us 20, and moving it by 2 positions gets us 30. This shows how pointers can step through arrays, accessing each element in turn. To wrap up, it's important to remember that arrays and pointers, while closely linked, aren't identical. An array is a fixed collection of elements with a set size, while a pointer is a variable that stores an address and can change where it points. Arrays can't be reassigned, but pointers can. This distinction matters when working with memory and data structures.
Thank you for watching my video. For more videos, please do like, share and subscribe my channel.